All right, we're going through example 3 in the proof by induction packet. In this case, we are asked to prove by induction that 1 squared plus 2 squared plus 3 squared up until n squared equals 1/6 of n times n plus 1 times 2n plus 1. We want to show that this is true for all positive integers n, which means we have to start at 1. So first we have to begin by proving the first case. First case is when n equals 1, so we'll sub 1 in for the general formula here. 1 squared is 1, so that doesn't change down our left-hand side. Subbing in 1 for all of these n's on the right. We've just got a 1 in the first parentheses, 1 plus 1 in the second, 2 times 1 plus 1 in the third. Doing some simplifying, actually all of these are multiplied so they can go on top of my fraction. 1 plus 1 is 2 in the second parentheses. 2 times 1 is a 2 there, which plus 1 becomes a 3. The 2 and the 3 cancel with the 6 to be left with just a 1 on the right-hand side, just like the left. Check. Second step is our assumption step. We're assuming that the statement that we're trying to prove is true for all positive integers. The only thing we have to do is change all of our n's to be k's. Third step, we're going to be using that first strategy that we talked about above, where we're going to add one more term on the left side and also on the right, right? Because we're squaring each of the terms on the left, we have to now square k plus 1. So I'm adding k plus 1 in parentheses squared on the left and on the right. Left-hand side won't change for the rest of this time. On the right now, we have to turn this to look like my original right-hand side, but have k plus 1s in all of these cases where it was originally a k. This is going to be a little bit trickier to do, but again, because my right-hand side is all factored, I'm going to try to factor out each of the different parts that I need. Originally, we have a 1/6 on the left, so I'm going to factor 1/6 out of both of these two terms. Put it there, and now I'm just going to introduce some square brackets to help me differentiate them from the other brackets. Next, I had a k originally. I want this to be a k plus 1, so I'm going to factor a k plus 1 here out of both of the terms. This one already has a k plus 1 that goes off on the left. My k times my 2k plus 1 is still on its own. Then over here, I already have two k plus 1s because they were squared. So one of them comes out front, the other k plus 1 stays there. Next, this k plus 1 is going to have to end up being a k plus 2, right? K plus 1 plus 1. In that case, I don't see any k plus 2s in either of my terms left in my square brackets, so that's less than helpful, which means I'm just going to recombine all of these and try to factor it normally on its own, which actually isn't too bad. This k distributes there, this 6 distributes in there, then I'm going to combine my like terms. K plus 6k is a 7k, and this is just a basic quadratic, which we know how to factor using a bunch of different methods that we've talked about before. You can factor that factors into k plus 2 times 2k plus 3. The k plus 2 is perfect because that's exactly what we need. We need k plus 1 in parentheses plus 1. And then my 2k plus 3 is going to be 2 times k plus 1 in parentheses. If this 2 distributes in, that would give me 2k plus 2. So I also have this plus 1 at the end, which was good because at the very beginning, it was supposed to be 2k plus 1. And now that former k is changed into a k plus 1 there. Now, all of these k plus 1s can be replaced with n's, just like I'm used to. So my original statement is true when n equals k and when n equals k plus 1, which means I can summarize at the end and say that by the principle of mathematical induction, this entire statement is true for all positive integers.